Before getting to the next algorithm, let me review what we have shown so far, because it has been a long way to get to the lemmas and the theorems that we wanted to prove. So we wanted to solve robot motion planning. To do this, we had the idea of enlarging the obstacles. Later, we could see that we could solve, if we enlarge the obstacle, we could solve it in a time complexity that is n log n, where n is the total complexity of the scene. Okay? But we don't know how complex the scene will become once we enlarge the obstacles. Okay? To enlarge the obstacle, we define the notion of Minkowski sum. We haven't still proven that it's the same thing, but we're going to get to it in a moment. Then we discussed the concept of pseudodisk, and we showed that if you have a bunch of pseudodisks of total size n, then the complexity of their union is O of n, or at most 2 times n. Then, not surprisingly, we show that if you create the Minkowski sum of two convex polygons with the same convex polygon, then the resulting two polygons are pseudodisks. So this and this are pseudodisks. So they intersect at most twice, and we have proven that as well. Okay. And finally, we saw that if you have an obstacle that is not convex, you can decompose it into a bunch of triangles. And now each one of them is convex. So therefore you could form the Minkowski sum of each one of them with this robot, and then take the union of them. And since the union of a bunch of pseudodisks essentially has linear complexity, it follows that the Minkowski sum of the robot on each triangle has complexity m. You have n of them, so in total that would be n times m. Okay? And we saw that this is tight. But now the question is, how do we compute this? Okay. So in other words, we have, let me go back here. We have this polygon P, and then we have this polygon R. We know that the Minkowski sum of them has complexity n times m. And we can compute each one of the components of this union. In other words, we can take this triangle, we can take the ith triangle, say delta I. We can look at the Minkowski sum of delta I and R, and we can get this shape that is enlarged delta I. And then we could look at, we know that their union has linear complexity. But now the question is, how do we compute that? One way to compute this is to do a sweep line approach. But unfortunately, sweep line, a naive implementation of a sweep line gives you n squared complexity. Let me explain why this happens. So imagine that you enlarge each one of these triangles. So this triangle will look something like this, let's say. Then this triangle will be enlarged and look something like this. Let's say. Then this other triangle will be enlarged and look something like this, and so on. As you see, there are lots of intersections between the segments of these enlarged triangles that are completely inside the union. We don't care about them, but potentially there could be n squared of them. If you do a normal sweep line approach, you will need to define an event point for each intersection point. And since there could be n squared of them, that will give us an n squared algorithm. So even though the union has linear complexity, it is not obvious how we can get an n squared algorithm. So instead, we're going to try to get an n log squared algorithm, where n is here is the total complexity of the union. Or in particular, we assume that m is a constant. So if m is a constant, then O of n times m that we had from before will become just O of n. So we do that for simplicity. Okay, but the solution doesn't actually need this. If you don't assume that m is a constant, then m term will appear somewhere over here, like as a multiplicative factor, I think. Okay, so how do we do this? This is actually a very interesting question, and maybe you can pause the video for a little bit to think about this. Because the solution is actually extremely simple and extremely elegant. Okay, so this is the problem, right? We have computed qi, which is the unique sum of the I triangle plus bit r, and then we want to compute this union. Right, so ready, here it is. This is the algorithm. We want to compute the unique. This is the function is called k parameters, where k is the number of things we want to union. If there is only one object to union, then there's nothing to do, so we can just return q1. Otherwise, we take the first half of these objects, q1 up to k half, union them, we get some shape A. Oops. And then we do the same with the second half, we get shape B, and then we return A union B. And that's it. So now the question is, why does this algorithm run in n log squared n time? To see that, let's look at the components of this algorithm. Okay. First of all, we have two recursions here. Okay. So therefore, if I want to write, so I'm going to get to this in a moment, to these two recursions. But then, so in other words, these things are not very mysterious. When it comes to analysis, it's mysterious, but it's not mysterious on what happening here, it's just recursive call. The one thing that's slightly mysterious is this one. How do we compute and return A union B? Okay. Well, A is some object like this, and B is some object like this, right? So they could be arbitrary. How do we compute the union of A and B? Well, here the observation is that A and B, since they are the boundaries of these objects, first of all, they have linear complexity. In other words, the complexity of A1 is n1, the complexity of B is n2, where n1 is the total complexity of q1 plus plus q and k half, and similarly for n2. Okay. This follows by our assumption, or by the lemma that shows the union of a bunch of pseudodisks has linear complexity. And obviously we know that n1 plus n2 equals n. Why? This is because well, this is every object is only is either here or here. Okay, so this is obvious. So now we compute the union of A and B with a sweep line algorithm. The genius of this approach is that we are now ignoring everything that is inside N2 and everything that is inside N1. We have already deleted them. And now we claim that the only intersections that exist between N1 and N2 are the boundary intersections. But this is essentially follows by definition, because N1 is the boundary of A. Oh, sorry, A is the boundary of the first half and B is the boundary of the second half. So whenever you have two boundaries intersecting, you get the boundary of the union. So that means the total number of intersections is O of n. And now if you follow the n log n algorithm for the intersection of line segment intersection, you get that we have an algorithm that runs as n plus k, well I shouldn't use k, let's use t, where the number of intersections times log n. Okay. What is t here? T is O of n based on what we have observed. So that means this algorithm runs in O of n log n time. So what we have shown is that no matter how this division is done, this is O of n log n. So now we can write recursion. We have f, so let's say t of k equals 2 times t of k half plus O of n log n. What does this solve to? By Master theorem, this solves to O of n log n times log k. Initially k equals n, so therefore this solves to n log squared. And that's essentially is the algorithm.